So, I'm really excited to present to you a project that I've been working on over the past few months, which is a sampler instrument for the Sounds of Scala library. For those unfamiliar, a sampler instrument is a type of digital instrument designed to play and manipulate samples of audio. And Sounds of Scala is a web-based audio and music library built for Scala. I implemented the sampler using functional programming, which is why I'm presenting it to you today. Now, a quick disclaimer, this is my first time speaking publicly and I'm extremely nervous, so I want to thank you. I just wanted to say that I appreciate your understanding and patience, and I hope everything goes well. Hi, I'm Johanna Odersky. I'm a junior Scala developer. I have a background in fine arts and music production. I recently started my first role as a Scala developer and have been contributing to Sounds of Scala in my free time. I've also been trying to keep up my artistic practice, which consists mostly of making objects, like this painting on folded canvas, or this public art installation I made on Lake Geneva. I also produce and perform music under my alias Iku. Since 2015, I've released 2 albums and several EPs, and I've had the chance to play in art and music venues across Europe, in the US, in Russia, and in Japan. My musical practice relies heavily on the layering and processing of samples, which makes this project meaningful to me not only as a developer, but also as a musician. So, why would one want to build a Scala sampler? Why use Scala for this endeavor? Scala is known for its powerful functional programming features, but it's not often associated with creative fields. But functional programming isn't just a coding paradigm, it's a style of thinking. And this style of thought is not only great for writing clean and efficient code, it can inspire and even shape creative processes. Now, music is emotional and sensory, but it's also structural. It fits the functional style of thought. You can think of musical structures, musical elements like chords, harmonies, rhythms as data structures upon which one can do a bunch of transformative functions on to create new musical elements. And music is full of weird mathematical patterns that somehow hit the same logical sweet spot as does working with functional programming, at least in my opinion. So I think we can see why Scala lends itself to creative fields, but I think now the question is how can we use Scala and functional programming concepts in creative fields? And I hope that this talk is going to give you one possible answer to that question. Here's a quick overview, so you know what's coming your way. I'll start by giving you some context on sampling as a musical tool. I'll talk a little bit about Sounds of Scala library. I'll go through one of the sampler's features, which I implemented using functional programming. And then I'll attempt to apply a functional way of thinking to music composition, so we'll make a little sketch of a song together. By the end of this talk, I hope that you'll have learned something either about functional programming or music, but in the best case, I hope that you'll feel inspired to use the sampler and Sounds of Scala yourself to create something. All right, so sampling. What is a sampler? A sampler, on the most basic level, is a digital instrument that plays back pre-recorded audio. It dates back to the 40s and 50s when experimental composers wanted to create new sorts of sound, and for that they explored sound as a material. So they took magnetic tape and they tried manipulating it in different ways. So they would trim the tape, loop the tape, reverse the tape, stretch the tape, compress the tape. So playing around with the time parameter, basically, of this recording to create new kinds of sounds. When plastic cassette tapes became mass-marketed in the 80s, hip-hop popularized the practice of sampling. And today it's a fundamental part of most musical genres. At its core, sampling is about using pre-recorded audio as musical building blocks. You can use this technique to build beats, melodies, soundscapes, sound effects, pretty much everything. And today's digital samplers actually still emulate the kind of material processes that were once used on magnetic tape. So in modern samplers, you will have features to crop the sample, reverse the sample, loop the sample, stretch the sample, compress the sample. So again, these kind of features to play around with the time element of the sample. So sampling is a fundamental tool in music production nowadays. So of course, we also needed one for Sounds of Scala. Now, Sounds of Scala is a web-based library. It's a library for building web-based music applications. Its main goal is to make creating music with Scala fun and accessible. By framing technical aspects of functional programming in a creative context, it's also great for education because it makes maybe certain aspects of functional programming more accessible to people. It has a stack of Scala.js, Scala 3, and Typelevel Cats. For those unfamiliar, Scala.js compiles Scala code into JavaScript, which means we can write client-side web applications while still keeping all the benefits of Scala, so strong type system, functional programming capabilities, and expressive syntax. Now, Sounds of Scala is not just a music tool. It's also a way for developers to look at functional programming through the lens of music. Sorry, I forgot that. Sounds of Scala targets the web audio IPA with Scala.js to bring audio processing capabilities directly into the browser, which again makes it very accessible. Now, the project is still in its infancy, and we're always looking for new contributors, so I'll be sure to share the link to the repo at the end of the talk, and you can get involved if this sounds interesting to you. Okay, I think we have enough context to start talking about the sampler. Now, depending on what kind of music you want to make, the way that you would employ a sampler can change significantly. So if I want to make some instrument that imitates drums, let's say, a drum set, I would try to take different samples of sounds, map them to keys or pads so I can play them like I would a drum set. But the model that we're focusing on today is going to be a sampler that links samples to musical notes. So we're going to have to adjust a sample's pitch and its playback rate in order to map one sample and play one sample across a musical scale. This is useful for when you want to imitate more melodic instruments like a piano or a guitar. But before we talk about repitching samples, we have to talk about the structure behind musical pitches. And actually, Chris already mentioned a bunch of this stuff yesterday, but since there's no better way of learning than repetition, I think it's going to be okay. So, as I said before, music is sensory and emotional, but it's also structural. This structure becomes clear when we look at how sound and acoustics work. Musical notes and their intervals, so the distance between notes, are defined by mathematical ratios. For example, an octave follows a 2-to-1 ratio. So if we want to find the frequency of the octave of a note, we multiply its frequency by 2. Meaning the higher note has twice the frequency of the lower note, its sound waves oscillate twice as fast. An octave, which is the same note but higher, is an octave only because we perceive the sound to be the same note but higher. And we perceive the sound to be the same note but higher because it sounds very harmonious and very complete. And that is thanks to its simple 2-to-1 ratio. Every musical interval can be broken down using these ratios. And it turns out that the intervals with the simplest ratios are also the ones that we perceive as being more harmonious or pleasant. Here's an example of a perfect fifth, which has a 3-to-2 ratio. Sounds pretty pleasant. And in comparison, here's a tritone, which has a 45-to-32 ratio. So this one creates more tension to the root note. It's also called the devil's interval. So you can see that the intervals that have a ratio that we would consider mathematically beautiful or harmonious are also the ones that we perceive as sounding harmonious. They align with how our brain interprets harmony. And when musical elements become maybe more complex or complicated, we tend to think of them as more dissonant. I find this intersection between math and the sensory experience of music really fascinating, which is why I wanted to include it in my talk today. Without knowing much about music theory, we can intuitively experience the mathematical structures that are woven into music. But of course, any attempt of theorizing music and our experience of hearing it is subjective and dependent on its context. So if we use non-Western music scales, or if we descend into the abyss of microtones, terms like harmony will need to be renegotiated. Anyways, in Western music, the smallest interval is a semitone. It's the distance between any two adjacent notes on a scale. In frequency terms, it represents a ratio of the 12th root of 2. And using this ratio, we can calculate the frequency of any note relative to a given base frequency. In Scala, that calculation would look something like this. We can calculate the frequency of a musical note based on the distance and steps to its reference frequency. So we multiply that reference frequency by 2 raised to the power of the number of steps divided by 12. You don't have to memorize this formula, but it's important to understand what it does because we'll use the same calculation to repitch our samples. So I'll show you how that works. In our sampler, we associate our sample, here stored in an audio buffer, with a key to identify which note on a musical scale the sample represents. That's because we need a reference note that we can base our calculations on when we want to repitch the sample. Can you see this okay, actually? Okay. Let's say I want to create a sampler that sounds and works like a piano. I recorded a C3 note on my actual piano, and when I instantiate my sampler, I map it to a sample key. The sample key corresponding to C3. Now, if I want to play the sampler on a C2, I'll need to repitch the frequency of the C3 sample. The way one changes the pitch of a sample is by adjusting its playback rate, which is the speed at which the sample is played. In basic sampler models like the one we're talking about today, these two are always linked. So if you change the playback rate, it will always affect the pitch. That's because when you change the playback rate, you're speeding up or slowing down the entire sound wave, including the oscillations that determine pitch. So a faster playback rate will compress the sound wave, increasing the frequency of the oscillations and raise the pitch. While a slower playback rate stretches the waveform, lowering the frequency and lowering the pitch.
It's quite literally how cassette tape works. So if in the 90s you played around with
tape and you fast forwarded one, for example, you would have noticed that everything became very high-pitched, creating this sort of chipmunk effect. Or a more contemporary example, nightcore remixes. Now, sorry, I just have to drink something. Okay, back to our example. We have our reference frequency of C3, and we want to lower it to C2, so 1 octave lower. I think we can guess by how much we have to multiply our playback rate with to achieve the C2 pitch. We multiply it exactly by half, which means the sample will play at half the speed, doubling its length, and repitching the frequency to C2. I think you can probably see the issue here. Since the sample length grows exponentially, pitching it over a large interval can result quickly in extremely long or extremely short samples. There are techniques to deal with this, like granular synthesis, but today we're going to address this issue by providing more samples for the sampler to choose from. So, we give our sampler a whole octave of samples from C2 to C3. And let's say I want to play the key D2 sharp, which is somewhere in the middle of all these samples. If the sampler has the choice between several samples, it will want to choose the sample with the frequency which is closest to the one we want to play. Now, how am I going to go about finding that sample? The sample I want to use as a base for repitching. First of all, let's order our samples by frequency. When a sample needs to be played, the sampler transforms our map of samples and their respective keys into an array of tuples containing the frequency, the key, and the buffer, ordered by frequency. Now we can use our helper function to find the sample in our new array with the frequency closest to our target frequency. We're using a binary search algorithm for this. And that's all you need to know. So, when I want to play my note D2 sharp, my sampler calculates the goal frequency of D2 sharp, finds the sample with the closest frequency to our goal, divides the goal frequency with the closest frequency, which results in the ratio that we'll need to multiply the playback rate with, and passes that ratio on to the method that actually plays the sample. That method then multiplies the playback rate by that ratio. And this method is also the method that will have to interact with the browser's audio interface, and along with the method that loads the samples, it's the only function that reaches out into the outside world and is therefore considered impure. I wrapped these I/O effects in I/O monads to deal with it in a functional and predictable way. And I asked ChatGPT to make this beautiful picture about impurity for me. Now, we have a functioning functional instrument that plays a sample across a musical scale. I think it's time we can put it to use. When we think about functional programming, we often picture an input being processed by a series of transformer functions, which then produces an output. For us, the input is going to be chords or a scale, and the output is going to be a melody. We'll use we'll use compositional algorithms that align with functional programming principles to generate said melody, and we'll try to make it sound musical. I've implemented an arpeggiator method to demonstrate this. An arpeggiator is a music tool that breaks down a chord or a scale into individual notes and plays them in a rhythmic sequence or a pattern, similar to how a prism refractors light into its component colors. Let's start with something simple to warm up. I have this chord progression of C3, C minor, F minor, G minor, and I want to arpeggiate those chords. What we'll do first is break down the chord into a list of notes, and once we have the notes separate as individual notes, we can use those notes to create an arpeggio. To create an arpeggio, we basically just need to adjust the note's offset. The offset of a note is the time before it starts playing. It's usually 0, because if I hit a note on an instrument, I want the note to play immediately. But in our case, since we got a chord with several notes playing at the same time, we want to change the offset to the offset of the note before plus the note's length to play them one after each other. So let's listen to how that sounds like. This is the chords without the arpeggio. And this is the notes with the arpeggio. Cool. Now, let's do something a bit more complicated. Let's give a scale to the arpeggiator. I chose C minor just because I like the scale. A scale is a sequence of musical notes ordered by pitch, typically spanning an octave, and it serves as a framework that one can use as orientation to create melodies and harmonies that fit and sound right together in a scale. This is the scale of A major. Now, we follow a similar path as we did with the chords, calling the arpeggiate method with a different set of parameters. And this time I'd like to use a bit more of a complex pattern for the arpeggio. So, since we want to use a functional programming approach, I decided to implement Pascal's triangle to generate a pattern for the arpeggiator. Pascal's triangle is inherently recursive. Each number in the triangle is derived from the sum of the two numbers directly above it. And in music, recursion allows for self-similar structures or repeated patterns, making this algorithm perfect for arpeggiators. Now, to create our pattern, we have to map our musical notes of the scale to the numbers in Pascal's triangle. This is what the triangle looks after we do that. We use the same method as before to create the arpeggio, so to play the notes in sequence, and this is what it sounds like. Cool. I think that sounds pretty good. I think there's too much repetition though, and I think there could be more variety in the rhythm and the spacing between the notes. So, I'm going to address both of my points of criticism at the same time by filtering out a note if the note that was played before is the same note, and replacing it by a rest, or also called silence. This is what our triangle looks like now. The underlined notes are the ones that we're playing, and the other ones are the silences. Let's have a listen. Okay, I think I'm happy with that. I think to add a bit of symmetry in the melody, I'm going to play that sequence again, but in reverse, after it played once. And I'm also going to combine it with my other arpeggio, the one we did in the beginning. And hopefully that will create some kind of sketch that sounds somehow musical. So let's have a listen. Oh wait, hang on. Thank you. So now you know what Pascal triangle sounds like. It might not be a Bach symphony, but I think if you tweak around with it a bit more, it might actually become something that you might enjoy listening to. I personally found the melody generated by the triangle quite interesting. It's definitely something I wouldn't have come up with myself. And the fractal recursive nature of the triangle gave the melody a dynamic, evolving quality, which I think is also pretty special. So that's my example of how it sounds like to apply functional programming thinking to music composition. With functional programming, you can express musical ideas very directly. It works well with the set of mathematical patterns that are inherent to music. But this was just one example, and functional thinking can be applied to all sorts of areas. Functional programming allows you to perceive and think in a structural way, which might come with unexpected beauty or patterns as a side effect. So I hope that there will be many more examples of how to apply functional programming to creative fields, and I can't wait to see what people come up with. I told you in the beginning that I would share the link to Sounds of Scala, which is here, and I also put a link to my SoundCloud in case you want to listen to some of my music. And yeah, this was very short because I talked much faster than I intended to. But anyways, thank you so much for listening.